Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is the summer 2020 offering of ECE3084 Signals and Systems. Previously in this course, we looked at sampling from a Fourier point of view, and what I would like to do here is look at it again from a Laplace point of view. Now, back when we looked at Fourier transforms, what we did is we took our incoming signal and we multiplied it by an impulse train going from minus infinity to infinity that took samples every capital TS samples apart. Actually, let me make this S look more like a subscript. Because we're in the realm of looking at unilateral Laplace transforms, because I didn't want to have to deal with all of the mess of dealing with regions of convergence that show up when you use bilateral Laplace transforms, I'm going to change this lower limit here to be n equals 0, and we're just not worrying about what happens for the function for t less than 0. So we'll call the resulting function x sub s t, where this represents taking samples, and that's going to look like a sum of x in capital T sub s, because if you multiply a function by a delta function, the only place the function matters is where the delta function is located. So we'll have this sample of our function times t minus n capital Ts. And we used a little abusive notation previously that said we could write the sample as x using brackets around the n. So that's just a shorthand, so you don't have to write TS all over the place. And this is also amenable to the way computer programmers who are used to writing in C and related languages like to think. So if we have a function going in that looks a little something like this, remember we are starting this at t equals 0, then the impulse train looks a little something like this. So when we multiply these functions together, we wind up with something like this. And this x of s of t is still a continuous signal. We just have 0 between these Dirac delta functions. This doesn't represent a physical sampling process. There's no integrated circuit you can buy from Maxim or Texas Instrument or Analog Devices in which you'll open it up and find a multiplier like this and some sort of impulse train generator. This is a conceptual mathematical model to help us reason about sampling. So let's see what the Laplace transform of x of s is. When I looked at sampling in the Fourier transform part of the course, we used a specific property that we derived. Here in the Laplace transform section of the course, I actually have a different goal, so I'm going to tackle this a little more directly. I'm going to go ahead and just write out what the Laplace transform integral is and stick all of this stuff in there. So the function I'm plugging in here is the sum from 0 to infinity, x of n times delta t minus n capital Ts. And this is all times my integration kernel, which is e to the minus st, differential with respect to time. So this x of n doesn't have any t's in it. So I'm going to pull this sum over n out in front. And then when I pull the integral inside, and when we simplify this expression, I can plug in capital Ts in for t, because that's where the delta function turns on. And then I can pull this constant out in front, and then I'm integrating over a delta function, which is guaranteed to be included in the integral. So I'm left with a sum of x of n times e to the minus s in capital Ts. Now, I hope you won't mind if I rewrite this in a slightly odd way. I want to write this as e s capital Ts to the power of minus n. So this is the same. Okay, so let's take this e to the power of sts and give it a name. Let's just assign a variable to it so we don't have to write e to the sts all the time. There's a bunch of letters we could use. There's a bunch of standard English alphabet letters. Mathematicians commonly use Greek letters. We could use a smiley face. let's use a standard English alphabet kind of letter. And for no particular reason, how about let's use the letter Z? Z is a nice letter. Let's rewrite this integral like this. We'll write n going from 0 to infinity of x of n, z to the minus n. Oh, that looks kind of neat. How about let's make a minor abusive notation and write this as big X of z. Yes, indeed. We have seen that before. At least you have if you took ECE 2026. This is, in fact, the Z transform. So one view of a Z transform is that it's a special case of the Laplace transform for sampled signals with a custom notation that makes some operations with the Z transform particularly convenient for the analysis of discrete time systems. So this expression here gives us a nice mapping from the Laplace plane to the Z-plane. If I take the logarithm of both sides, I can start to come up with a formula going the other direction and write S equals log of Z over capital TS. Now, there is some major strangeness going on with this logarithm. Right now, I'll just draw an arrow to it and I'll just write careful in big scary red color. Before we continue, let's play with this Laplace transform a little bit more. Let's ask, what happens if I take my S and then add J times some integer K times 2 pi over capital TS? This 2 pi over capital TS, we could also call that omega S, which would be the sampling frequency in terms of radians per second. So I'm going to take all of this and plug it in for S up here. So I would have my sum times my x of n of e to the minus, here will be S plus j, k is some integer, 2 pi over ts in capital TS. And now I can split the exponent. I can write this as e to the minus s in capital TS, t sub s, times e to the minus j k times n, 2 pi, and the ts's cancel in this factor. But remember, k and n are both integers. So here I have e to the j, 2 pi times some integer. So this is all going to give me 1. And what's this expression? Well, it's the Laplace transform x of s that we had earlier. This tells us that all of this stuff is equal to big X of s times s. So essentially, in the same way that sampling in time resulted in replication in the frequency domain, sampling in time in the Laplace domain context involves replication vertically on the S-plane along the imaginary axis. And it makes sense because that imaginary axis corresponds to frequency land, which is what Fourier transforms involve. So all the stuff you do with Z transforms, you could do with Laplace transforms, but Z transforms are a whole lot more pleasant to work with than Laplace transforms for discrete time systems.